So welcome back, and today we will start with the third module. Okay, so in the syllabus, module 2 is regarding Laplace transform. So we'll be seeing module 2 after completion of module 3. That is how it should move, because Fourier series is defined for periodic signals, and Fourier series which was defined for a periodic signals is known as Fourier transforms. And there are certain signals for which Fourier transform does not exist. For that, we multiply with a convergence factor so that we get a new transform, that is Laplace transform. So Laplace transform is actually that should come after third module. So I'll be taking Laplace transform, that is the second module after completion of the third module. Okay, so right now we'll start with the Fourier series representation. So Fourier is a French mathematician. So he had described the Fourier series. It had its own controversy in the beginning while he established Fourier series. I'll come to that later on. And before going into the Fourier series representations, we have two types of representations of Fourier series. One is in terms of sinusoidal functions, and other is using trigonometric functions. Okay, so two types of representation. One is the sinusoidal function type of representation, and the other is the trigonometric function representation. So first we'll see Fourier series in terms of sinusoidal functions of time. Okay, so before going into the representations or Fourier series, I have to just place why we should learn Fourier series. See, you are learning now the linear control system. Okay, so last two classes we have learned about the convolution integrals and convolution sum, which were defined for an LTI system, that is linear time invariant system. Let us assume a linear time invariant system having real parameters or constant parameters. For instance, if you take an RL circuit or an RC circuit, if you apply the input as a sinusoidal voltage, you get output as a sinusoidal voltage. Okay, so when we apply a sinusoidal input to such a system, such an LTI system with constant parameters or real parameters, we'll get output as another sinusoidal waveform with a function h of j omega or of h of s. You'll understand this a little bit later. That is, if we give a sinusoidal input to an LTI system with real parameters, the output will be another sine function multiplied with a function called h of j omega. That h of j omega or h of s is known as the transfer function or the system function. So the output is also sinusoidal function, which is multiplied by h of j omega. So h of j omega has its own magnitude. So the thing is that the input and output are both sinusoids, but the difference is that the output is a transformed sinusoid, which is having a different magnitude, that is a magnitude of h of j omega, and it will be having some different phase. If initially the phase of the input was theta, then the output sine wave will have a phase like theta plus alpha. Okay, and the sinusoid waveform will have a different magnitude, that is the magnitude of h of j omega. So thing is that the conclusion is that, see, when we apply a sinusoidal waveform, we get a sinusoidal waveform with that is a transformed sinusoidal waveform. Transformed sinusoid waveform in the sense it is having a different magnitude and a different phase compared with the input sinusoid. So the crux is that if we apply sinusoidal waveform as an input, output is also another transformed sinusoid. So that means if we have two sinusoids, it is very easy to get the transfer function or the system function. System function is nothing but the mathematical model of the signal system itself. That is, we can assume an LTI system with lumped parameters or real parameters or constant parameters. So we are defining a mathematical model in the form of a system function or a transfer function by applying a sinusoidal waveform and getting a transformed sinusoidal waveform. Okay, so that is how the sinusoidal waveforms are very important. Okay, so if we apply sinusoidal waveforms, we get a transformed sine wave. Okay, now the question is, can we extend this concept for any periodic functions which are non-sinusoidal? Okay, The answer is S. Why S? The answer is S because this is done through the Fourier series representation. That is, any arbitrary periodic functions which are non-sinusoidal can be, that is actually two examples are shown in the note itself, that can be written as a sum of a DC value and so many sinusoids. Okay, and that is what is Fourier series all about. That is, I repeat, any arbitrary periodic non-sinusoidal waveform can be represented as a sum of a DC value or an offset plus so many sinusoids. That is how it is written as f of t is equal to a naught plus a1 cos omega naught t plus a2 cos 2 omega naught t plus it continues like that, and the last term of that series will be an cos n omega naught t plus b1 sin omega naught t plus b2 sin 2 omega naught t plus and the last term of that series will be bn sin n omega naught t. Okay, now we can write it in a short form, that is a naught plus a naught is nothing but the DC value or the offset plus summation from n is equal to 1 to infinity an cos n omega naught t plus summation from n equal to 1 to infinity bn sin n omega naught t. Okay, now these are defined for periodic functions, and you know what is a periodic function. Periodic function, if f of t is periodic, then f of t should be equal to f of t plus t naught for all values of t, and I have shown a waveform with a period of t naught. Okay, and what is t naught? T naught is the smallest value which satisfies f of t is equal to f of t plus t naught. Why? Because 2 t naught, the waveform which I have shown there, can be periodic with a period of 2 t naught also. It can be periodic with a period of 3 t naught also. Okay, but that is not the time period. Time period is the smallest t naught, smallest time for which f of t is equal to f of t plus t naught. And if you know the period, then of course you can get the value for frequency. Frequency is nothing but 1 by t naught, and if you know f naught, then you can get the angular frequency omega naught, which is nothing but 2 pi f naught. And there is one more representation for that Fourier series representation, that is, it is C naught. C naught is nothing but equal to A naught plus a summation from 1 to infinity 2 Cn cos n omega naught t plus phi n, where Cn is nothing, where 2 Cn is nothing but root of an square plus bn square, and we will come to that in a later stage. That is why it is 2 Cn is equal to root of an square plus bn square. We'll come to that in a later stage when we represent the Fourier series in the other way. Okay, and what is the phi n? Phi n is tan inverse of minus bn by an. Okay, and a naught, as discussed, is equal to C naught, which is the DC component of the signal. Okay, now which is the fundamental component? Fundamental component is nothing but when n is equal to 1. When small n is equal to 1, we get the fundamental component. So fundamental component is nothing but a1 cos omega naught t plus b1 sin omega naught t. So sum of these two fundamental components will give the fundamental component 2c1 cos omega naught t plus phi 1. And what is the nth harmonic component? Nth harmonic component is nothing but an cos n omega naught t plus bn sin n omega naught t, which can be written in the form represented earlier, that is 2cn cos n omega naught t plus phi n. So fundamental component can also be termed as the first harmonic, but usually we say it say it as fundamental component, and the nth harmonic is represented as an cos n omega naught t plus bn sin n omega naught t. Okay, so I told that there were some controversies when Fourier, the French mathematician, first established this Fourier series, because he told that it can be extended to any arbitrary periodic sequences, or any arbitrary periodic sequences can be written as a sum of so many sinusoids. Okay, but you see the second waveform, that is a square wave. A square wave is periodic waveform, it's non-sinusoidal, but you can see that there are so many discontinuities. That is, at the point when it reaches the maximum value, that point is where there is a discontinuity. At the point when it comes down from the high value to the low value, there is another discontinuity. So a sine wave, for a square wave is completely with discontinuities. So a signal with so many discontinuities can also be represented with so many sinusoids which are continuous in nature, or a waveform, even a waveform with so many discontinuities can be represented in terms of so many continuous terms of time, continuous terms in time domain, which stirred off so many controversies, but rest is history, because we know that today Fourier series is an integral part of engineering field, and and many applications are based, or many analysis are done based on Fourier series. Okay, so that is one thing, and we have to, obviously there are three questions to be answered. That is, first question is, for is Fourier series applicable to all periodic signals, all what are the types of signals for which Fourier series can be applied? Okay, the complete set is not known, but one thing is sure: Fourier series is applied for, or defined for, all periodic functions. Okay, then the second thing is that if you see the series f of t is equal to a naught plus infinite summation. I am taking it as an infinite summation because n is going from 1 to infinity, an cos n omega naught t plus another infinite summation of bn sin n omega naught t. So you have to grapple with so many terms, an infinite number of terms. So how to calculate the values of an and bn? An itself will lead to infinity, and bn also will lead to infinity. Leading to infinity in the sense a1, a2 up to a infinity, and b1, b2, b3 up to b infinity. So how can you work with such a infinitely long series? Or if you want to work with such a infinitely long series, how to find such a huge amount of terms, an ranging from 1 to infinity, bn ranging from 1 to infinity? That's a big question. And the third question is, if it is possible, then how will you evaluate a naught, an, and bn? Okay, and the answer to the first question I have already given. That is, what is known is that Fourier series is defined for all periodic functions. Okay, and the answer to the second question is that, see, you can truncate the series at an appropriate point depending upon the accuracy you require. See, accuracy you require, I'll explain using the waveforms which I have drawn in the note itself. See, one thing is known, that is, the first fundamental signal, that is a1 cos omega naught t plus b1 sin omega naught t, will have the maximum amplitude. For the second term, that is for the second harmonic, that is a2 cos 2 omega naught t plus b2 sin 2 omega naught t, the frequency increases, or the frequency doubles, but the amplitude reduces. Likewise, for the third harmonic, frequency is multiplied by 3. The fundamental frequency is multiplied by 3, and but the amplitude goes down. Okay, and so you can see that as the harmonics progresses, or as the value of small n progresses, the frequency increases, but the amplitude or the magnitude of that signal decays or decreases progressively. So there is no point in taking harmonics or values of n, or terms associated with certain harmonics beyond a certain value of small n. Sometimes you can take up to n is equal to 29, or sometimes you may have to take you can take values up to n is equal to 49, but beyond that you can see that the values after n is equal to 49 will have negligible amplitude. So accounting or adding such a signal with negligible amplitude will not make any sense. So you can wisely take a decision to truncate the series at an appropriate point, so that the accuracy you require is met with. Okay, so that is clarified with the figures shown in this page. That is, you are actually having a square wave of equal amplitude. That is, 1 is the height for the positive side and -1 is the height for the negative side, and we are taking one time period. And you can say that if you take the average value of that square wave for one time period, it's 0. That means a naught, the average value, the a naught DC offset is 0. Okay, so That is why a naught is not considered, because when you take the average of square wave, it is 0 for a cycle. And if we add only the fundamental term, that is a1 cos omega naught t plus b1 sine omega naught t, then you can see that dotted square wave there. And that is the fundamental is nothing but a full cycle of a sine wave. Okay, full cycle of a sine wave, half cycle comes for in the half cycle of the square wave, and the next half cycle comes in the negative half cycle of the square wave. Okay, that is one full half cycle. And when we take n is equal to 3, that is when we include fundamental, second order harmonic and the third order harmonic, then that is terms of a1 b1, terms of a2 b2, and terms of a3 b3. If we add all these 6 terms, or you can see such a waveform for n is equal to 3, that is 1.5 oscillations in the positive half cycle and 1.5 oscillations in the 1.5 cycles in the negative half cycle. So 1.5 plus 1.5, 3 cycles of oscillation altogether in that one time period. And you can see that from when we compare n is equal to 3 slide with n is equal to 1, you can see that this waveform is coming more closer to the square wave. And now consider the case when we add up to the terms till fifth harmonic. Then you can see that 2.5 cycles are in the positive half cycle and rest 2.5 cycles are in the negative half cycle. So total cycles are 5. And so you can say that again, when you compare with n is equal to 3, again it is coming very close to the square wave. And if you and the last slide, if you add terms till 49th harmonic, see, if you add terms till 49th harmonic, you cannot see the dotted lines. It is very close to the square wave. You can see that after adding such terms till 49th harmonics, the square wave approaches. The square wave approaches the resultant series, added series approaches the square wave. Okay, so you can take a decision when to truncate the sequence according to the accuracy you required. That is the answer to the second question. And the third one, if it is possible, how to calculate the values of a0, an, and bn. Okay, so we have to, before going to the calculation of a0, an, and bn, we have to work out some background integrals. Okay, so the range of all integration is actually taken for one full cycle, one full period, starting from any arbitrary instant t1 to t1 plus t0. So that's, if t1 is 0, then it will be integration will be from 0 to t0. So in general, I am considering the integration for one complete time period from any arbitrary instant t1 to t1 plus t0. T1 can be 0 as well. If it is 0, then the limit of integration will be from 0 to capital T0. Okay, so the first background integration is that of cos n omega naught t dt. And if you know that if you find the average value, if you find the integration of cosine wave or sine wave for a complete time period, then it will be 0. So that is the first result, that is integration of cosine wave as well as sine wave over a complete time period is 0. Okay, then the second term, that is if you find the integration over a complete time period of a product of sine m omega naught t cos n omega naught t, that is integration from t1 to t1 plus t0 of a product, that is sine m omega naught t cos n omega naught t dt, then the result is actually half integration from, that is I am using the identity, half integration from t1 to t1 plus t0 sine n plus n omega naught t plus sine m minus n omega naught t. That is, you can say that it is all 0 for, that is, after all you are performing the integration of S2 sine waves. Okay, so if m is equal to n, what happens? If m is equal to n, then sine 0 is 0, so that is again 0. So for all other values of n, you have a multiple, an integer coming, so that integer is multiplied with omega naught t. So again it repeats the first case that we have discussed, that is integration of a sine wave over a complete cycle. So for all values of n and n, m and n, the value of this integration is equal to 0. Now we see the third case, that is if you find the product of two sine terms, that is sine m omega naught t sine n omega naught t dt. And if you integrate over a complete time period t1 to t1 plus t naught, you can see that again you apply the identity, it will be half integration from t1 to t1 plus t naught cos m minus n omega naught t minus cos m plus n omega naught t dt. Okay, you can see that for all m not equal to n, for all m not equal to n, you can see that omega naught is multiplied with an integer. So that means that again two cos terms similar to the result of the first. So what happens if you integrate over a complete cycle for that cosine waveform, that will be equal to 0. So it will be equal to 0 for all m not equal to n. Now what happens when m is equal to n? So for m is equal to n, for the second term, that is m plus n becomes 2m or 2n, that is again an integer, so that again becomes 0. But what happens to the first term, that is cos m minus n omega naught t, that is for m is equal to n, that is cos 0 is 1. So 1, if you integrate from the limits of t1 to t1 plus t naught, the result will be t naught by result will be t naught, and outside you have a half, so that becomes t naught by 2. So the result is that of the third background integration is that is the result is 0 for m not equal to n, and it is equal to t naught by 2 if m is equal to n. Okay, now similarly for the fourth background integration, that is if you find the integration of two cos terms, that is if you integrate cos m omega naught t cos n omega naught t dt over a complete time period t1 to t1 plus t naught, then similar to that, if m not equal to n, that is equal to 0, and if m is equal to n, that will be equal to t naught by 2. Okay, so these are the background integrals we require before we go to the evaluation of a naught, an and bn. And we recall what is f of t. So what is f of t? It is a naught plus summation an cos n omega naught t plus bn sin n omega naught t. Now for the first for finding the value of a naught, the first thing, that is we are integrating the above equation both sides with respect to t for a complete time period. I take it as 0 to t naught for simplicity, 0 to t naught. So 0 to t naught f of t dt equal to 0 to t naught a naught dt plus what happens to the all cosine terms and what happens to the all sine terms. We apply the background integration result of 1, that is if we integrate sine terms, and cosine terms for one complete cycle, that will be 0. So all second and third terms will be 0. So and we know that that is equal to a naught is a constant, so the result is actually a naught t naught. So from that you can find that the value for a naught. A naught is nothing but 1 by t naught integration from 0 to t naught f of t dt. So what is a naught? A naught is nothing but, we know that's a DC value. DC value is nothing but average value. So average value of f of t over one complete period is nothing but a naught. So what is a naught? Average value of f of t over one complete time period, that is 1 by t naught integration from 0 to t naught f of t dt. Now the second integration, that is we multiply f of t with cos f of t with cos n omega naught t dt, cos n omega naught t on both sides, that is multiply throughout the equation, that is f of t equation with cos n omega naught t, and integrate that resultant thing with over one complete cycle from 0 to t naught. Okay, so everything is multiplied by cos n omega naught t. So a naught is also multiplied by okay. So when a naught is multiplied by cos n omega naught t, what happens? A naught is a constant, and if you are integrating a cosine waveform over a complete cycle, so that becomes 0. So what about the second term? Second term is nothing but that is integration from 0 to t1 an cos n omega naught t cos n omega naught t dt. Okay, that is, see why I have taken, see that is an infinite summation, that is summation an cos n omega naught t. With that we are multiplying cos n omega naught t. Okay, see I have taken, see you're actually using the result of we are actually using the result, fourth result, that is fourth result, that is consider the fourth result, that is this integration exists only when m is equal to n. That is here, even if we are having infinite number of terms, the terms only one term exists, that is the term with a value n will exist, that is it will have a1 cos omega naught t, it will have a2 cos omega naught t, it will have a3 cos omega naught t, and we don't know what is the value of small n. Okay, sometimes the value of n will be 5. So the term a5 cos 5 omega naught t cos 5 omega naught t will only exist, because that is where we have m is equal to n. Okay, so only the nth term will exist, only the term which is actually equal to n terms will exist, all other terms will go to 0. So the result is that result is an multiplied by t naught by 2. So from here an is nothing but 2 by t naught 0 to t naught f of t cos n omega naught t dt. Okay, similarly you can write the third one, that is bn also, that is 2 by t naught 0 to t naught f of t sine n omega naught t dt. So these are the that is the terms a naught, an and bn, where we represented the f of t in sinusoidal terms. Okay, so with this I conclude today's class, and in tomorrow's class we will see some more modification, that is we will see halfway symmetry and all other things, and we'll solve 2-3 problems also after that, and thereafter we'll be moving to the trigonometric form of Fourier series. Thank you.